Hi everyone! So today we're going to build our first TVC controller prototype together. I'm totally not recording this video for the second time because I screwed up the focus on the first time, but well, nobody's perfect. This August we were busy constructing this. This is our engine gimbal. Currently it's built to hold two 38mm motors from Caesaroni. That's far enough for our first launch. That will give us about 300 to 400 meters of altitude, and we can test our TVC there before we go over to our very big engines, which are 75mm engines that can carry us up to 6 kilometers. That's a completely different house number. Is that even saying? I don't care. Basically this is just two motor pipes on a gimbal with two axes. One axis right here and one axis connected to the rocket right here. Both axes are moved by linear servos. Like for example this is stolen from a CD drive. So over here you see a small DC motor, and over gears it moves about the reader head of the CD drive. That's basically what we're going to use as well, but definitely not in that size. To move around our engines we're going to need about 100 to 200 newtons on each axis. So the axis that is connected to the rocket will be powered by a 300 Newton linear servo, and the inside axis is going to be powered by at least 250 Newton servos. They will be connected to the little bits you can see over here. These linear servos run on 12 volt DC, and they do suck some amps, so we cannot just feed them from our Arduino or, in our case specifically, Raspberry Pi 03. So we are going to use these. These are called motor drivers. Specifically, these are TLE5206 motor drivers. They can run up to 5 amps at 40 volts. They have two digital inputs with which you can decide the direction the motor which is going to be connected runs in, and obviously outputs, ground, and all the other funny pins. We're going to use 2 of them in our today's build. In reality, we might use more of them. They also have an error flag pin coming out, so if anything goes wrong, overheating or shorting of the wires, these error flags will turn on, and we can decide, for example, to switch over to a backup motor driver. Our linear servos also have potentiometers inside of them. These are used to measure how far the motor is extended. For our test purposes, we're going to use 2 potentiometers which are being turned instead of being pulled and pushed. They function exactly the same way, just circular, not linear. As these give off analog signals and our Raspberry Pi can only take digital signals, we will need a translator. We are going to use this. This is an MCP3008 analog to digital converter. It has 8 analog input pins, and on the other side you have all the beautiful pins like voltage, ground, and an SPI surface. You can use it to up to 3.6 MHz, which is definitely far enough for us, and we're going to use it to translate the information we get from the potentiometers into a language the Pi understands, which is digital. And then, last but not least, we need this little bit. This is a DC-DC converter. Because we have at least 2 power cycles, a 12 volt cycle for the motors and a 5 volt cycle for all the logic units, we're going to need something that translates the voltage between them. This is an LC78, and it can turn anything from up to 30 volts down to exactly 5 volts with throughput of about 2 amps. In our rocket design we're going to have one common ground, so no differentiation between the ground for the 12 volts, the 5 volts, analog or digital ground. So we are going to connect up all the ground wires on this board. Then we need the 2 power cycles. I decided that the upper line is going to be our 12 volt power cycle and the lower part is going to be our 5 volt power cycle. So let's connect that up too. We're going to start with the motor drivers, which I moved over a little bit to have more space. The middle pin of them is going to be the ground pin. You might have noticed they have a total of 7 pins. 3 pins are bent this way and 4 pins are bent this way. So the middle pin is still, well, the middle pin on this side, which is this one. going to connect them up to ground. Then our motors are running on 12 volts, so we are going to have to connect up 12 volts to our power input, which is going to be the third pin on the lower side. So 12 volts are up there. We're going to have to take a little detour over here to connect it properly. Next thing, the error flag pins are digital pins, but they can only be set to high, so 5 volts. If they're switched off, they will not be set to 0 volts, so ground, they will just be open. So we will add a pull-down resistor to ground, so we will not get weird information on our pi. So that is that done. Next we're going to move over to our analog translator. First of all, it has two grounds, a digital ground and an analog ground. Both of them are going to be the same ground on our board. Next we need the power supply to the chip, so that's 5 volts. And we need a reference voltage for the chip to which it can compare the analog input voltages, which in our case is going to be 5 volts as well. The 4 pins left now are clock, chip select, input and output, which is the SPI interface we're going to connect to our test CPU later. On the other side we have all the analog input pins. We only need 2 of them, and for the other ones to not show us weird numbers, we're all just gonna connect them down to ground. So we only have 2 pins left open, which is the 0 and the 1 pin, which we both will connect up to our potentiometers. Sadly, the color coding of our bridges is not perfect, as the color is a reference to the length of the bridge and not what its use is, so I tried my best, but this one over here is just going to be a little bit colorful, but just note that this one is going to be plugged into the pin 0 and this one is going to be plugged in to the pin 1. Next up we need to finish the connection of our potentiometers, so they both need a ground on the output side and 5 volts on the input side. So now what happens if I turn a potentiometer? Depending on where it's turned, it will give us an output voltage between 5 volts and 0 volts, which we directly compare to the 5 volts as a reference voltage in the chip, and we will get a digital output on how high, essentially which percentage of voltage is coming in, giving us the direct number of which percentage the motor is going to be extended. Now all that is left is to connect up our DC-DC converter. It has 3 pins, voltage input, ground and voltage output. We're gonna start with voltage output, which is going to be 5 volts over here. Then our pin to our common ground. And then our voltage input, which is going to be 12 volts, which is over here. When dealing with something like motor drivers or especially DC-DC converters, you have to note that the voltage they output is very unusually just a flat, perfect voltage. There are big ripples or small ripples, and they might damage the electronics. So a way to get rid of that is capacitors, which we have over here. Our DC-DC converter technically needs only 2 capacitors, a 10 microfarad capacitor and a 20 microfarad capacitor. I only have 10, so we're going to double up on one of the sides. One thing to note is that these capacitors have a polarity, so if you turn them the wrong way around, they literally tend to explode and smell very bad, so just watch out which direction is the right direction. So we need 10 microfarads on the 12 volt side, and we need 20 microfarads on the 5 volt side. Next up are the capacitors for our motor drivers. These are 100 nanofarad capacitors. They're supposed to be put in as close to the motor driver as possible, and they are connected to ground and the 12 volt input. And then we need 2 100 microfarad capacitors, which can be put in a little further away from the motor driver. Also here, again, polarity, watch the way you put it in, or it will explode up in your face. Which, by the way, nearly happened when I accidentally shorted the board on an earlier attempt, and you probably will not see it on the camera, but there's a definite bulge in the top of this. You can also see the cross pattern, which is there for the explosion to be directed upwards and the whole thing not blowing as a landmine, but just a little pop in one specific direction. But that's beside the point. So, this is pretty much our done setup. There's only 2 things missing. One is this. This is our motor simulator. I could have used these small DC-DC motors, but that was just too much work for pretty much no use. So I decided to just build this, which is 2 LEDs with diodes in front of them and resistors for it to run at 12 volts. The diodes, which only let through electricity one way, will light up one or the other LED depending on which direction our motor driver is trying to turn our supposed motor. There's 2 of them, one for each axis. The output pins are the very outside pins of our motor drivers. So there and there, and there and there. One thing you might have noticed is these potentiometers are not really solidly sticked into this, so we're gonna have to deal with some shaking and maybe some mismeasurements later. But that's just for the prototype and for the testing of the potentiometer system, so essentially the MCP3008 and its communication, so that's not too big of a deal. Our today's test CPU is going to be an Arduino Mega. You see, I already have all the cables put in. We're also gonna have a look at the code in just a second. Let me just connect it up. First of all, it runs on 5 volts, so 1 into our common ground and 1 into our 5 volt input. Over here there's 2 batches of cable. One is for our motor drivers and one is the SPI interface to our MCP3008. The purple wires are the arrow flag inputs from the motor driver, so we will connect them up. They're currently not respected in the code, there's nothing going on with them, but just for good measures we put them in. The green and the blue wires are each motor driver respectively, and the input of the motor drivers are the 2 inner pins on our 4-pin side. So here, and here, and here, and here. You see why I did the cables last, because there's quite a lot of cables and we would not see much of the construction underneath if I would have put them in earlier. Last but not least, the SPI interface. The white cable is our clock signal and the purplish cable is going to be our chip select. The orange cable is the input of the Arduino, so the output of the MCP, and the yellow cable is the output of the Arduino, so the input on the MCP. Next up, we're going to have a look at the code currently on this board. I would have written the code from scratch and uploaded it to the board together with you, but sadly a little mistake happened and I completely fried the USB on this board, so no uploading new code, but hey, the correct code is still on there, so at this point I would have said, so I'll switch over to the computer and show you what we got. But here's the bad news, that has to wait. Progress on the rocket is sadly just so slow that we cannot afford making the videos much longer without YouTube thinking we are simply dead. With this big to be continued, I will say goodbye for today. Thanks for watching. If you want even more information about our rocket, check out our website Atmoventus.space. You could say hi to us on Facebook, or if you want to see the next video, part 2 of this video much earlier than everybody else, join us on Patreon. We would be happy to see you there. Thanks for watching and bye bye!